Hi, this is Soikat Majumdar. Today we will start a new module, Statistical Mechanics. We will start with the topic Introduction to Statistical Mechanics. The learning objective of Statistical Mechanics is to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. Now, what is statistical mechanics? Thermodynamics deals with the macroscopic properties of the matter. Thermodynamics is not dependent on the fundamental nature of matter. That is, thermodynamics is valid whether the matter is made up of atoms and molecules or whether the matter is made up of some kind of continuum fabric. Now, quantum mechanics deals with the behavior of matter on the microscopic scale. In quantum mechanics, we calculate the energy and behavior of few atoms or small molecules. Most calculations are performed at t is equal to 0k. We can't get macroscopic properties, for example, EOS, that is equation of state, etc., from quantum mechanics. Now, statistical mechanics is a bridge between quantum mechanics and thermodynamics. We seek to use statistical mechanics to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. So, quantum mechanics that is not dealt with the macroscopic properties. Now, if we adopt statistical mechanics, so macroscopic thermodynamic properties can be well explained. Why study statistical mechanics? Let us consider an example. We have used equation of state. What are they? They give us a method of calculating one of the pressure, volume, temperature, given any two of them. Usually, equation of state are cast in some analytical function. How do we get equation of state? Get some functional form. P is equal to function of volume and temperature, V and T. For example, Van der Waals made the guess that P is equal to RT by V minus B minus A by V square. Measure as much PVT data as we possibly can done for specific fluid. Regress the parameters in the EOS, that means equation of state, in some least squares fashions. For example, we have to find A, B in the Van der Waals equation of state for fluid. Do you now have complete information? How about U means internal energy, H, S and enthalpy, heat, total H is the heat, S is the entropy. What happens if you want to find EOS of a different fluid? For example, you did the above for propane. Now you want the EOS for H2O. In many cases, you need to go back to the beginning. That is, gauge a new functional form. This is because you can't fit propane and water with the same functional form. That means we cannot use a particular functional form for different liquids, say for water, for propane, etc. So we have to adopt different functional form. Problems with the above process. Number one, very time consuming and very expensive. Number two, have to start all over again for many new fluids. Number three, extrapolation outside the region of parameter regression is not valid. Extrapolation often gives unphysical results. For example, what happens in the van der Waals EOS if V is equal to B? Number 4, this process does not give any physical insight about why the fluid behaves as it does and how symmetrically improve the equation of state. And last, you do not know anything about many of the other properties. Is there some way we can get the equation of state from fundamental approach? If matter is truly composed of molecules, then it must be the interactions among these molecules that give rise the macroscopic observable behavior. The postulate, if we can understand the microscopic interactions, we can predict the macroscopic behavior. This is the goal of statistical mechanics. That means from understanding the microscopic interactions, we can predict the macroscopic, or we could predict the macroscopic behavior of the system. Now, statistical mechanics can be divided into two types of statistics. One is classical statistics, another one is quantum statistics. Maxwell-Boltzmann statistics fall under classical statistics, and Fermi-Dirac statistics and Bose-Einstein statistics fall under quantum statistics. What is classical statistics? If the properties and laws of motion of individual microparticles can be explained by classical mechanics, we call it classical statistics. Already we have said Maxwell-Boltzmann statistics is the classical statistics. The quantum statistics, if the properties and laws of motion of individual microparticles can be explained by quantum mechanics, we call it quantum statistics. It is also, we have stated, Fermi-Dirac and Bose-Einstein statistics are quantum statistics. The classical statistics explains successfully many physical phenomena like temperature, pressure, energy, etc. of a system, but it fails to explain adequately several other physical phenomena such as black body radiation or specific heat at low temperature of a system. This phenomena can be explained by quantum statistics. Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics will practically give the same result at higher temperature and low pressure. This is to be remembered, very important. At higher temperature and low pressure, MB, BE and FD will practically give same result. Energy levels and energy states. So this is a figure. There are K, L, M, N different shells. So we will represent, these are the first one K, energy level 1, maximum number of particles 2, then energy level 2, maximum number of particles 8, electron is 8, energy level 3, maximum number of electrons 18, this is 32 and so on. So thermodynamic system is always associated with some discrete energy levels in which a large number of particles can be accommodated. Any energy level, large number of particles can be accommodated, large number of particles, 2, 8, 18, 32, this. Any energy level of a system is characterized by principal quantum number n. Generally, each and every energy level is associated with a large number of particles, and all the quantum numbers n, l, ml, ms for any two particles are not identical. Thus, there are several states for a given energy level. The several states corresponding to a given energy level are called energy states. The several states given to a corresponding to a given energy level are called energy states. Here we can see from n is equal to 3, transition of particle from n is equal to 3 to n is equal to 2, this red line. From 4 to 2, blue line or blue sheet. 5 to 2, violet sheet. So the electron energy normally expressed as 13 minus 13.36, 13.6 by n square. Now if n is changing, suppose for n is equal to 1, for n is equal to 1, E becomes minus 13.6 eV. N is equal to 2 means 4, then E becomes 3.34 eV. N becomes 3 means 9, E becomes minus 1.5 eV. So these are the ionization energies of this electron in different states. N is equal to 3, N is equal to 4, N is equal to 5. The ionization energies are different. Now, here we can see the different energy levels. This is ground state, then another state, or first excited state, second excited state. This is. Suppose for this ground state there is only one energy value. This is a non-degenerate state. For first excited state there are 3 states having same energy value. 3 states having same energy value. So this is a degenerate state, and degree of degeneracy is 3. Degree of degeneracy is 3. For second excited states, suppose there are 5 states having same energy value. So this is then the degree of degeneracy will be 5. Now come to the mathematical part that can be understood easily. In 3D cubical box of width A, the energy levels of the particle, we can write it as Enx Ny Nz as h square by 8 ms square. H means Planck's constant, m means mass of the particle, a means width of the potential well. Nx square ny square nz square. Now in the ground state, nx, ny, nz is equal to 1, 1, 1. That means nx is equal to ny is equal to nz is equal to 1. So its value becomes, energy eigenvalue becomes E11 is equal to 3h square by 8m square. So this is the lowest energy states for a free particle in a cubical box, and it is non-degenerate because it has only one energy value and only one wave function. Only one wave function. For the first excited state, there are three quantum states with quantum number 211, 122 and 112. For all these 211, 122, 112, putting this formula, E becomes, energy eigenvalue becomes 6h square by 8 ms square. That means energy eigenvalue is same, but the functions are different. So here in first excited state has threefold degeneracy, and this state is a degenerate state. Come to the second excited state, where the quantum states, quantum number are 221, 212, 122. Here for this 221, 212, 122, the energy eigenvalue becomes 9h square by 8m square. So here also the energy eigenvalues for these different quantum numbers, energy eigenvalues are same, 9h square by 8m square. And the functions are, there are three functions, three wave functions. So second excited state has also threefold degeneracy. Come to the third excited state. Now the quantum state with quantum number 222, so this becomes 12h square by 8m square. There is only one value and wave function is only one, so it is a non-degenerate state. It is a non-degenerate state. But here the degree of degeneracy is 3. Here the degree of degeneracy is 3. Now let us come to the main part of the statistical mechanics with some conceptual definitions. First one is isolated system. It is a system of particles which does not interact with any other system. So that its total energy is constant. That means it is a system of particles which will not interact with any other system. So system of total energy of this system is constant. Now macrostate. An isolated system containing a fixed number of non-interacting identical particles having fixed internal energy. That means N is fixed, E is fixed, and occupying a fixed space of volume, that means V is also fixed, is said to be a macroscopic state or macrostate of the system. Now what is microstate? The number of meaningful ways in which the total energy E of the system can be distributed among its constituent particles are called microstates. Now consider an example. Here we have considered two distinguishable particles, each of which can be in one of the three energy states, and the energy states are epsa, 2 epsa and 3 epsa, with total energy is 4 epsa. The combinations of the particles are given as. It is shown in the table. First combination is there are two distinguishable particles. Suppose total energy should be 4 epsa. So suppose we have placed one particle at the epsa energy and another in 3 epsa energy. Here there is no particle. So this one is epsa into 1 means epsa, 3 epsa into 1 means 3 epsa, 3 epsa plus 1 epsa means 4 epsa. Another combination is there are only two particles, both these two particles at the 2 epsa energy states, and there is no particle at the epsa and 3 epsa energy states. 2 epsa and 2 means 4 epsa, so total energy becomes 4 epsa. So here we can find the total number of microstate as 2. One is 101, another one is 020. So the possible combination is 2 of the particles, so that the condition can be satisfied. That means two distinguishable particles, they can be in between the 3 energy states, so that the total energy becomes 4 epsilon. This is a possible combination. Now consider these particles are denoted as A and B. The possible microstates for various particles. Microstate means number of meaningful ways. The particles can be distributed in different macrostates. So the possible microstates for various particles in the macrostates are like this: 101. Suppose 101 two particles A and B. In the epsa energy state we have placed A. There is no question of putting it in, that is 0. So in 3 epsa state B. Now alter this, B is here, A is here. So there are A0B or B0A. There are two microstates. So for this macrostate 101, there are two microstates. For 020, that means two particles in the same energy state, A into B, AB, A and B. These are the two particles. These are the same energy state 2 epsa. So this microstate will be 0, AB 0. So there are only one microstate. So for two particles, distinguishable particles that are denoted by A and B, for macrostate 101, the number of microstate is 2. For macrostate 020, the number of microstate is 1. So in our case, in our example, there are total microstate is 3 and total number of macrostate is 2.